is Martin Gutoski. I work for a company called Kongsberg Discovery, which is headquartered in Norway. So we have a very long history. It's actually not 400 years, but 200, but still. And that is 200 years of determination, 200 years of innovative breakthrough. We are a global player and a digital forerunner. So Kongsberg is actually headquartered in a place called Kongsberg, which means the King's Hill in Norwegian. And we started business in the mining industry, doing silver mining in the mines of Kongsberg. And then we moved along with the Norwegian state over the period of 200 years. And we have been supporting the Norwegian country and the Norwegian government with its endeavors. So when oil was discovered back in the 1970s, Kongsberg was the company supplying the technology for the oil exploration, and we have been doing this innovation forefronting ever since. Just some words about the company. So we are more than 12,000 employees operating in 40 countries with an annual revenue of more than 30 billion Norwegian kroners, which is about 3 billion US dollars. And we are operating in 4 business areas, which are Kongsberg Maritime, Kongsberg Discovery, that I'm representing today, Kongsberg Digital, and Kongsberg Defense and Aerospace. We are a strategic company in Norway, so we are majority owned by the Norwegian state. So we are traded on the Oslo Stock Exchange with just over 50% of the shares held by the Norwegian government. In Kongsberg Discovery, we concentrate our endeavors on ocean technology. We have SeaTechs, which do positioning systems for the maritime industry. We have uncrewed platforms, maritime robotics, and marine life technology that is dealing with commercial fisheries. Kongsberg Discovery itself is about 1,000 employees, 3.5 billion Norwegian kroners order intake, and we are the technology backbone of the company. The global reach in this area, we have as Kongsberg a large office in Busan, close to the shipbuilding industry. I myself am based in Singapore, which is the hub for the Asia-Pacific markets, and further offices in Japan, in Shanghai, and in Australia. We provide technologies for secure and sustainable oceans. Working with the Sustainable Development Goals, which have a large part of it to do with maritime. And in particular, we are looking at the initiatives. We are in the United Nations Decade of Ocean Science for Sustainable Development, running from 21 to 30. And there is an initiative by the Nippon Foundation, JEPCO, Seabed 2030, which is looking at mapping the world's ocean until 2030 in a relevant resolution, which we are supporting and a part of. In actual fact, there is the annual conference next week in Fiji, which we are supporting and attending. So how do we contribute as a company? By providing sensors. So the journey with our sensors started back in 1947 when a gentleman called Willy Simonsen founded Simonsen Radio, known as Simrad, which was later acquired by Kongsberg. And he used the technology that came out of naval applications during the Second World War, sonar technology, for applications in the commercial world. So the first application was fishery sonars, detecting fish, and then later on using the technology for mapping the oceans, mapping sonars, which we still do in a continuous process of developing and bettering them. But the sensors are just a part of the puzzle. We believe that integration is the key. As a company, we provide many pieces of the puzzle, but the magic lies in integrating these puzzles into an operation, and the integration means efficiency for safe and efficient maritime operations. So we integrate with the bridge system, with the automation on a vessel. We provide the propulsion and the connectivity to make the vessel work as one unit. Another important technology development over the last years and the years to come is autonomy, marine robotics. When they came onto the market, maybe 30, 40 years ago, they were able to provide data that you were not able to obtain in any other way. So it was about data and data quality. And nowadays it becomes more of a force multiplier. So you use the robotics in parallel with your traditional methods to have more reach, have more bandwidth, and produce more data to high quality and efficient ways and faster than you would be without the robotics. If you have many platforms deployed, your marine robots, your traditional vessels, you need interconnectivity. So data transmission and remote operations is another aspect of technology development. And then most importantly, digitalization. Bringing the information to the cloud, to the end users of the technology in the format that they can understand. So you deliver information to any stakeholder in any place, in any kind of format that is needed, and that is running under digitalization. So this is how we see it. We start with the sensors, integrating them into a system, bringing autonomy into play, interconnectivity of the three, and then bringing everything into the cloud to make it available in the format that is needed. To give you some examples, the sensors we are talking about, Kongsberg Discovery provides multi-beam sensors that are used to map the ocean floor. We have a large customer base here in Korea with the major research institutions and the mapping authority. And we provide these on the research vessels that are built in Korea, and they are operated by the institutions here in Korea. This is the data that we provide. This is an example of a latest system which shows a car wreck. So this is the type of information you can obtain from these type of sensors. And different water depth up to the full ocean depth. So we have been involved in a project called the 5 Deep, which went out to map the deepest points in the ocean, in the world oceans. So this is an example of the Mariana Trench, which is the world's deepest point in the Pacific Ocean, called the Challenger Deep, and our systems were used to map these. And there was a human expedition going down to this depth in the Pacific Oceans, and similar in the Indian Ocean, in the Atlantic, the Northern Ocean, and the Southern Ocean. Ocean science, providing information not only of the seafloor, but we use platforms, instrument carriers, mooring systems, gliders, autonomous uncrewed vehicles. We can estimate the biomass, which has always been important, but is increasingly important to take the right decision on harvesting and sustaining the the biomass and life in the sea. We looked for non-biological targets, oceanographic layers, currents, sediments, seabed classification, gas bubbles, marine hazards, which is all an important topic going forward. And these are the instrumentations that we use. Some examples of showing shoals of fish, and our sensors can be used to identify these. So you see the fish, you can estimate the biomass, and you can detect what species it is. So this is essential database for any kind of ecological research and management in the oceans. In addition, we can map the oceanography, so this is showing different layers in the oceans. And then going on to the second example, which is autonomy. And this is really taking off in recent years, and it will be the topic for the coming years when it comes to ocean research. So we have 30 years of experience in this field. So we have a product line called Hugin, and we had the first deployments back in the 1980s. We always collaborated with important stakeholders. So we collaborated with the Norwegian Defense Research Establishment and the Norwegian Navy, as well as the major commercial companies like Statoil, which is the Norwegian oil and gas company, which changed its name to Equinor. So these were partners from the beginning. And we had the first deployment back in the 1980s and are collaborating throughout the journey to have the evolution of the technology that we see today. So these are the underwater robots that we are talking about. They're called Hugin, and it's unmanned submarines, essentially. So the normal system, the standard system, can be rated from 3,000 meter depths to 6,000 meter depths. It has an endurance to 30 to 60 hours. It's 6.2 meters long and weighs about 2 tons. And then we are expanding the range to smaller units with less depth rating and less endurance. And to the right-hand side, that's what I want to concentrate on a bit today. It's the latest development, which is a long endurance vehicle, which can stay under the water and complete emission, fully autonomous for 15 days. And it's larger for the reasons I'm going to explain. So what do you do with these systems? You have a number of payloads. These are sensors to collect the data, which can be a multi-beam, which I showed you before, collecting information of the seafloor, mapping the seafloor. We have a synthetic aperture sonar, which gives you very high resolution sonar imagery of the seafloor, which is used in this case for detecting wrecks. Sub-bottom profilers, looking into the sub-bottom. Laser profilers, which gives you very high resolution. 3D maps of structures, like a pipeline in this case. And we have opticals, which is stills camera and movie cameras. So these are the data you can get out of it. It's very popular with the community looking for shipwrecks. So this is showing an example of shipwrecks on the seafloor with a lot of debris, which you can map to very high resolution. And this is the journey of the development of this system. So the initial design for the long endurance, we set out for it to work 15 days in a depth of 6,000 meter, with a focus on from shore to shore operations. So you don't necessarily need to have a vessel to launch and recover. You can launch it from the shore and collect it at the same point or at a different point on shore. increased focus on operational robustness and situational awareness, which is necessary if you are out fully autonomous for such a long period of time. Challenges to increase the endurance and the payload. We need to have the energy and the capacity on board. The vehicle concept calls for long missions without a support vessel, so it needs to be fully autonomous and needs to make decisions by itself, so artificial intelligence plays into it. And it's much more complex to operate and to plan missions with these systems. So the solutions we came up with, it's a free flooded architecture. So the housing is not pressurized. We have pressurized housing for the individual components inside, but not for the whole vehicle. It's powered by lithium-ion batteries, and it has multiple processors. The payload sensors, we stuck to what we know, the proven payload sensors, and we have the similar navigation architecture than the current vehicle. And we reuse existing pressure housing and have similar recovery mechanisms and the same sensor options as the previous systems. But what is different? The battery and payload capability needed to be increased. Redundancy, if any system fails, there needs to be a backup plan, and we have to have redundancy to keep the system operating autonomously for such a long time. The control system architecture has changed, and we have increased fault detection and handling. We have active control, and we have thrusters and a dual counter-rotating propeller to make the system more stable. And this is how it looks like. So the pressure housing for the storage, control electronics, and the payloads, and then the configurable base for battery and additional payloads. It has active ballasting, so this is important if you're working in different environmental conditions in terms of temperature and salinity in the ocean. You have to have different ballasting to counteract the environmental conditions, which we put in place. We needed more reliability and self-awareness and redundancy in the electronics, and this is what we came up with in the end. So the vehicle is 11.8 meters long. It has a diameter of 1.2 meter, 8 tons weight, a depth rating of 6,000 meters, endurance of 380 hours, about 15 days, and a speed range of 2 to 5 knots. A range capability of 2,400 kilometers, a navigation accuracy of 0.04% of the distant travels as the error of navigation. And we have a configurable payload bay of 1 cubic meter, and we can take 1.5 tons of payload. And it's designed to deliver payload as well. Not operate only on the vehicle, but we are able to deliver a payload, and that is specifically important or interesting for naval applications as well. So we set out to do this. We had a contract when we first set out to do it. So a customer gave us a contract for a system and asked us to develop it within 18 months. And we did it. So that was placed last year. So just September this year, 2 months ago, not even 2 months ago, we had the first mission of the vehicle. So the system stayed out for 16.5 days in a fully autonomous operation. So there was no communication or positioning update with the vehicle while it was operating. The water depth was in the North Sea, close to Norway, operating in water depths 50 to 3,400 meters. That's as deep as the North Sea goes. We covered above 2,200 kilometers, and the positioning error from when it dove down to when it came back up was 440 meters in actual position to where this system thought it would be, which equates to 0.2% of the distance traveled. And the data set required, it's full data sets, synthetic aperture sonar, multi-beam camera, and laser data. And it's a world record for autonomous operation on this scale. And this is concluding my presentation, and I would like to thank you for your attention, and I hope I could give you some information about my company and give you an example of what we are doing with a very recent example of a development of an autonomous system. So thank you very much.